Good evening, everyone. Welcome back to Fiveable's coverage of AP Statistics. This week, we will be wrapping up our work with sampling distributions that we started last week. Last week, we looked at categorical variables and building sampling distributions for p-hat. And this week, we will look at quantitative variables and build sampling distributions for x-bar, or sample means. As always, be sure to follow us on any social media platform that you so choose. And in this stream, we're going to do a simulation where we'll build another sampling distribution using a little online app. Remind ourselves what a sampling distribution is, define it, do some notation, view some formulas for mean and standard deviation in these cases. Look at the conditions for sampling distributions to be approximately normal, which remain the conditions throughout all of inference, whether you're building confidence intervals or hypothesis tests. And then comparing the results from last week with the results from this week. And then we can dig into some practice problems regarding sampling distributions. Big picture wise, okay, remember that the goal of inference is to gather information about an entire population using just a sample or samples from that population. And a lot of the times, the stuff the information you're going to try to gather about the population is not known about the population at the time that you take the sample. And so the statistic you get from your sample, whether it's a p-hat or an x-bar or a sample median or whatever you're trying to calculate, is going to provide the basis for estimating the corresponding parameter: population proportion, population mean, population median, in the given population that you're taking a sample from. And so on your screen, you see just a couple examples of common parameters in statistics that we work with quite a bit in AP Statistics. When we're working with a categorical variable, you're typically working with p and p-hat. And with means, quantitative variables, you're typically working with mu and x-bar. And last week, we built some sampling distributions for p-hat. This week, we will build some sampling distributions for x-bar. And without further ado, let's dig into it. So I'm going to switch screens, and we're going to go to a sampling distribution simulation. So let me get out of here, close this video, and we're going to share a different screen. That's the guy. Okay, so on your screen right now, you should see a normal distribution at the top of your page. And so we're going to pretend that this can be any quantitative variable in the world. It looks like the scale goes from 0 to 32. It could be any set of numbers, but we have a parent population. Because it goes from 0 to 32, let's just pretend this is a population of ACT scores for various kids at a school. Obviously, ACT scores can go up to 36, but good enough. We'll take it. So as you can see in this population, the mean is 16, the median is 16, standard deviation is about 5. It's perfectly normal. That is listed off to the left side of the screen. And what I'm going to start doing is taking very small samples of data out of this population. So I'm going to sample 2 individuals at a time. And you will see that happen. I just took a sample of 2 individuals, and then it dropped a little blue bar on the third line. So the second line is 2 individuals drawn from this population, and the blue bar is the x-bar, the sample mean of whatever those 2 individuals' ACT scores were. So it looks like the first person was maybe around 12, the second person's maybe around 20, and so that x-bar is maybe 16, something like that. It looks like it's in the same place as the overall population mean. Now, if I take another sample, I might not get the same 2 individuals again. In fact, I got much higher x-bar because I got 2 individuals on the right side of the population. Now I just got 2 more in the center. Now I got 2 slightly on the left. And at this point, I've taken 5 samples, each with 2 people in it, and plotted 5 x-bars. And so there are 5 blue dots that really get stacked into a single bar. So there's 2 x-bars that were the same, and then 3 x-bars have been unique so far for a total of 5. And what's going to start happening as I take more and more and more and more samples, I'll skip ahead to doing 5 at once. And so now we're at a total of 30 samples of 2 individuals, all drawn from the same population. And I'm graphing out all the x-bars as a result of those samples. I'm going to skip way ahead to 10,000 samples. And what you should see is a really nice normal distribution of X bars, but not quite as spread out as the original population. And if you think about why that's happening, it's because when you take a sample of any two individuals from the population, when you average those results together, it's unlikely to be as spread out as all of the individuals are themselves. So if I pull one person from the very right edge of the population distribution, for my X bar to also be there, I'd have to pull a second person all the way on the very far right edge. And that typically doesn't happen. Typically, you'll get people from the middle, and so it will balance out. You notice the spread isn't quite as wide. Now, if I reset this, I've got the same population. It's normally distributed. ACT scores are normally distributed at this high school. But if I switch to 5 kids at a time, now I'm dropping 5 little black bars out of the top, and then it's creating a single blue bar for the X bar on the third row. This first X bar is very close to the actual population mean. Do another one. Okay, another one kind of close in the middle there, and I'm just going to skip ahead to 10,000 samples, and you'll notice another nice normal sampling distribution of X bars with a smaller standard deviation than the original population. And you might already know where this is going if I make the samples even bigger. Skip ahead and go right to 10,000. Yep, another nice normal distribution. The center's right about the same spot, but a smaller standard deviation. And if I'll go one further, all the way up to n equals 25, now I've got a really normal distribution with a really small standard deviation of X bars. Very interesting. So anytime the original parent population was normal, it looked like the sampling distribution of X bars also ended up normal, no matter what the sample size was. But as sample size went up, the standard deviation of the sampling distribution went down. It was always lower than the original population standard deviation. One thing to point out before we go any further here is there's a clear distinction between population distribution, which is at the top, sample distribution, which is the 5 people I just pulled from the population, and sampling distribution, which is being built with the blue bars on the third row. Population distribution is all the individuals you could be looking at. Sample distribution is the individuals you pull from the population in your individual sample. And a sampling distribution is all of the X bars you get from all of the different samples you pull. So if I pull 10,000 samples, the blue graph now has 10,000 X bars graphed on it, all of the same sample size, in this case, n equals 5 people, from the original population. Whew, lots of vocab terms. You might be wondering, though, what happens if I take samples from a different type of original parent population? This time, the population is skewed pretty heavily to the right. So you can see the mean is a little over 8, just to the left of that original graph. It tells us the mean. The median is 7. So the mean higher than the median. That's because the skew is to the right. Mean is higher than median when you're skewed to the right. Mean is lower than the median when you're skewed to the left. Let's see what happens to my X bars when I take very small samples. So if I just take a sample of 2 people, I got 2 people from the right side there. Kind of surprised by that. Okay, now I got one from the very far right and one from the very far left, average out to be right in the middle there. And you can see I'm building another sampling distribution of X bars. They don't seem to be as spread out as the original parent population. And 10 samples in, I'm getting pretty mixed results here. If I skip ahead and do 5 at a time, okay, starting to build up a sampling distribution and starting to look like it might end up being skewed. I've taken 56 samples so far, each of sample size 2 people from this original population. And it's not quite looking the same as the original population. Let's skip ahead. All right, 10,000. So this time, I see that my sampling distribution is still a little bit skewed to the right. But the standard deviation is lower than the original parent population's standard deviation. Not entirely surprising there because of what we saw last time. Let's clear this out and do sample size of 5 at a time, see what happens. Taking samples of 5 individuals from this skewed right population and building the sampling distribution of X bar. Again, each of the 5 things dropping out of the top line represent individuals pulled from the population. And then the blue line that gets dropped on the 3rd row represent the X bar from those 5 individuals. And if I skip way ahead, oh, okay. Smaller standard deviation, still a little bit skewed to the right when I look at it. Not quite perfect here, but it is starting to look a little kind of symmetric even with my sampling distribution. Now, if I go to 10 individuals at a time from the population, you'll see I can pull 10 dots this time, start dropping some X bars. And if I skip right ahead to a bunch of samples, oh my goodness, the standard deviation is getting lower and it's not as skewed as it used to be. That sampling distribution is starting to become a little bit more normal. Let's bump up to n equals 16. Okay, smaller deviation, becoming a little bit more normal. Let's go all the way up to n equals 25 and skip way ahead. And now I have an almost, it's not quite all the way there yet, but that sampling distribution is almost approximately normal when the original parent population was skewed to the right. And that's kind of interesting. And this is a really, really, really big deal what we're seeing. I've on the slides here, I've got this app linked to the slides, and you can I'll put them in the comments on the stream if you're watching on replays. You can go play with this, because the cool thing you can do with this is you can actually build your own custom distribution. So I can make this crazy bimodal graph that's almost uniform and just looks really ugly. And you can see the same thing as you start to take samples from this distribution. Even with just n equals 2, my sampling distribution looks crazy all over the place. And this makes sense. Most of the time you'll pull one individual from each side of this distribution. So it makes sense that the X bars end up in the middle, but it's not that unlikely that I end up with 2 from the same side of the population. And that's why I get those little mounds on the side. But as I start to take bigger and bigger samples, the sampling distribution is starting to become more and more and more approximately normal. And if this doesn't convince you, I don't know what will, of the following. I'm gonna come back. Well, I had a big punchline ready, but I'm gonna go back to the original slideshow. Share. All right, there we go. Okay, so we just saw this, the images on the right, we just saw a simulation of that. And so we just saw a sampling distribution. We simulated building a sampling distribution, which is the distribution of values taken by the statistic p hat or x bar in all possible samples of the same size from the same population. So I kept pulling the same number of individuals over and over again out of that original population. On the top, we see a sampling distribution we built last week with 25 samples or 25 candies at a time from a big candy machine where 50% of the candies were orange. And these were the p hats. And then one of my n equals 10 from the one we just did. The actual sampling distribution would have literally all combinations of all samples of the same size from the original population. We're not really going to do that much in real life. And each dot was a p hat or x bar. So hopefully the stuff on this slide makes sense to you watching back on replay. And what we are going to be often asked to do in AP Stats is describe the sampling distribution that would come from a certain scenario. And because the graph of x bars or p hats is a dot plot or a histogram, if you will, it's going to have shape center spread. And we saw that the shape ends up being approximately normal with certain conditions being met. We'll go over those conditions in just a second. You can calculate the mean of your sample proportions or sample mean, so mu of p hat or mu of x bar, and you can calculate the standard deviation of those things as well. So sigma of p hat or sigma of x bar, and that leads us to what we just saw. Even with the skewed distribution, when n was 10, I was starting to get a fairly normal, but not all the way there yet, sampling distribution of x bars. It turns out that to describe a sampling distribution of X bar, the shape is going to be approximately normal. If the original population is normal, you're going to get an approximately normal sampling distribution no matter what. And if the original population is not normal, like we had a skewed distribution population you can see on this one, if the sample size is at least 30, that's considered good enough, like widely accepted by statisticians, to say that that's going to give you an approximately normal sampling distribution. That's a large enough sample, large counts, to guarantee that the sampling distribution of X bar will be approximately normal. Not the same magic number as with p-hats. P-hats, the magic number was 10. We'll go over that in a little while. And then the center of the sampling distribution, the mean of all the sample means, should equal the population mean, while the standard deviation of sample means will be equal to the original population standard deviation divided by the square root of the sample size. Meaning, as I take bigger samples, I get a bigger number on the denominator. That means I get a smaller standard deviation of X bars, which makes sense. Every time I took more individuals from the population, my results should get more and more and more consistent, because outliers have a smaller impact with a big sample than they would with a small sample. So if I only take 2 individuals out of a skewed population and I get one of them from the skewed side and one from the non-skewed side, average them together, you'll still get pulled by that skew. If I take a sample of 20 people and one individual comes from the skewed side and the other 19 are coming from where the bulk of the data is, my X bar will end up much closer to where the bulk of the data is, as opposed to being affected by that outlier. And so the note that's made up there about n being greater than or equal to 30 is called the Central Limit Theorem, which says no matter what the original population looks like, even if you don't know what it looks like, if you're taking samples that are at least 30 individuals at the same time, the sampling distribution of X bars that you get from those samples will be approximately normal no matter what, which is pretty cool. And the bigger samples you get, the better the approximately normal shape will be. It says no matter what the original population shape is, sampling distribution will get more and more normal as n gets bigger. Pretty big deal. And to compare to last week, here's what we had for the same thing. So the way to get the shape to be approximately normal for p-hats, you need to see at least 10 successes and 10 failures in your sample, or expect to see that in your sample. And then if you're working with a quantitative variable, n's got to be at least 30. Those magic numbers are definitely things to memorize, because they are the conditions throughout all of inference. Sampling distributions, confidence intervals, hypothesis tests, no matter what you're doing, you want to see at least 10 successes and failures for proportions, and you need to see a sample size of at least 30 for means, or have evidence that the original distribution is normal in the case of means. And then you can see similar looking formulas for the mean and standard deviation of p-hats and x-bars, where the statistics, p-hats and x-bars, when you average them together, they should equal the original population proportion or population mean, which means that the statistics are called unbiased estimators. When I pull p-hats or x-bars from the population and average a bunch of them together, I should end up averaging out to the original population parameter, which is the basis for everything you do with confidence intervals and hypothesis tests, is all assuming that the sample you're getting is going to provide an unbiased estimate for the population that you're looking at. And you can see in both formulas for spread, n on the bottom, meaning sample size on the denominator, is a algebraic way of showing that as sample size goes up, results become more consistent because those standard deviations go down. So the bigger your sample, the smaller your spread is expected to be when you're working with different samples from the same population. So at this point, we've built a sampling distribution for X-bar. We built some sampling distributions for p-hat last week. We went through some facts about them. This last slide is definitely something that you want to write down. The center and spread formulas are on the AP Stats formula sheet. So you don't need to have them memorized, but you do need to have the symbols memorized. The conditions for being approximately normal are not referenced anywhere on any kind of formula sheet. So you do need to have those cases memorized as to how you get an approximately normal sampling distribution. Let's look at some scenarios to ask us to apply these facts. So off to the side here are some reminders for you. Here's a sample scenario. The distribution of the length of time it takes students to travel to class at a certain college is bimodally distributed due to some of the students living on campus and others having to commute by car or bus. So if you picture a graph where the length of time it takes to get to class is on the x-axis, bimodally distributed means you've got two clusters of individuals, probably some with very short commutes because they live on campus, and some with very long commutes because they have to drive, and there's probably a gap in the middle. So I'm guessing that the people who live on campus all probably take less than 10 minutes. Maybe the people who are commuting all take more than 20. And maybe no one's really taking 15 minutes to get there. But we're then given info that the population mean travel time is 26 minutes with a standard deviation of 12.5 minutes. 4 random samples of 100 students taken from the population describe the sampling distribution of sample mean travel time. That keyword describe, anytime you're talking about a distribution, whether it's a population or a sample or a sampling distribution, describe means that you should be talking about center, shape, spread, outliers. My class uses CUS as an acronym: center, unusual feature, shape, spread. Your class might have used SOX, shape, outliers, center, spread, or some of you just memorize the things to talk about. But anytime you're asked to describe a distribution, that's typically what you're being asked to do. And so all of our answer choices are going to give us a shape, a center, and a spread. And here are some sample choices. One of these is the correct answer. In about 20 seconds, I will reveal which one is correct based on this situation. Answer coming in 3, 2, and 1. Because of those formulas off to the side, if I recognize that 100 is my sample size, I can use that as n to calculate my standard deviation. And so the center of the sampling distribution should still be 26 minutes, but the spread will be much lower. Divided by square root of 100 leads me to 1.25. And the reason I can say that the graph should be approximately normal is because 100 students is bigger than 30. And if I'm taking samples of size 30, of greater than 30, it does not matter what the original population distribution is. The sampling distribution will be approximately normal. So my answer is D as in dog. And as an extension to this, new question this time, same setup. What is the probability that a random sample of 100 students will have a sample mean travel time of less than 25 minutes? So instead of asking you for a single individual taking less than 25 minutes to get here, like you might have done back when you were learning about normal distributions, now I want to know the chance that a sample of 100 students will have an X bar of less than 25 minutes. But since I just calculated the mean and standard deviation of X bars, and the sample size is big enough that I'm guaranteeing an approximately normal sampling distribution, this question is really asking me to find the shaded area on this graph here. Notice I've labeled a normal distribution with the mean of sample means and counted 3 standard errors or standard deviation of X bars away from 26 minutes. I wouldn't be able to draw this graph with the original standard deviation because it's a bimodal distribution. It's not a normal distribution. This graph is specifically for samples of size 100. If they ask me for samples of size 200, I'd have to calculate a new standard deviation of X bar using n is 200. To find this area, I can do it one of 2 ways, just like however you do it to find normal distributions. I like to use my handy dandy normal CDF button on my calculator once I've got a picture sketched and labeled. Others would calculate a z-score using 26 as the mean, 1.25 as their standard deviation, and 25 as the individual, getting a z-score of negative 0.8. Trust me, the math checks out. And then going to look at their table A normal distribution probabilities to find a probability. I would type it into my calculator using the normal CDF command, but either way I go, I'm going to find a probability of about 0.2118. So about 21% of all samples of 100 students would show an average travel time of less than 25 minutes in their sample. Cool beans. If you're at hypothesis tests already, you already know that that probability we just found could be interpreted as a p-value in a case of a hypothesis test involving a a sample being 25 minutes and comparing that to the null hypothesis of 26 minutes. If you don't know what I just said, don't worry. Tune in in about 3 or 4 weeks, and we'll be getting to those. So if you're ahead of me, awesome. Okay, so that's a couple of sample problems that use sampling distributions. The most common multiple choice problems ask you to do things like we did back here, where you're picking out what the actual shape is going to be, or what the description would be. Free response settings sometimes ask you to just describe the sampling distribution, which you then do what the choices were. You list a shape, a center, and spread, and then often ask you as a follow-up question to apply that description to a probability. It's not a super common thing on the free response, but it can come up from time to time. Probably about once every 4 or 5 years, you'll get a question asking you to describe a sampling distribution on free response. It's almost always about X bars and not P hats on free response. Multiple choice, it can go either way. But here's a summary. With no one here to ask further follow-up questions, I'm actually going to end the stream. Thanks for watching. We've been watching on video replay. What's coming up in the next couple of weeks is we're going to start digging into more inference and start building confidence intervals. So sampling distributions provide the foundation for everything you do with confidence intervals and hypothesis tests, because all the assumptions we make about, or all the calculations we make when we're building margins of error or finding Z test statistics, Z or T test statistics, to then calculate p-values from, is all based on the sampling distribution being normal with our conditions being met. So next week, we'll meet confidence intervals. We'll define what a confidence interval is and do a couple of just basic introduction things, but then really dive into building out some 1 and 2 sample Z intervals for population proportions or difference of population proportions. And then the week after that, get into the same thing with T intervals, which are for means. So I'll leave you with this final image, and with unfortunately no one here live, I'm going to wrap it up for the night. Thank you for watching on replay. For those of you that are watching, I will see you next time. Be sure to follow Fiveable. There should be some big announcements coming pretty soon about some opportunities. So stay tuned for those, and hopefully I'll see some of you in future weeks. Take care.